Module 1, Lesson 6, Algorithm. For this module, we will be covering the following. We will define algorithm, the different ways to express your algorithm, some sorting algorithms and searching algorithms, and finally, we'll discuss complexity of algorithms. What is algorithm? Algorithm is an effective method in solving a problem expressed as a finite sequence of instructions. These algorithms are often used for calculation, data processing, and many other fields. They usually start from a given initial state, and then the instructions describe a computation that proceeds through a well-defined series of successive states, eventually terminating at a final or ending state. There are several ways to express your algorithm, like natural language, pseudocode, flowcharts, or programming languages or control tables. What are natural language? Natural language expressions of algorithm tend to be verbose and ambiguous, and thus rarely used for complex or technical algorithms. This is one such example of your corresponding natural language. It gives off a set of instructions that are eventually in sequence, and this particular solution solves by selecting the largest number in a given particular finite list. So simply follow the steps 1 to 3 in order to determine the largest number in your given finite list. Pseudocode, flowcharts, and control tables are a more structured way to express algorithm because they avoid ambiguity. What is a pseudocode? A pseudocode basically provides an intermediate step between English language description of an algorithm and an implementation of this algorithm in a programming language. Programmers can use the description of an algorithm in a pseudocode to construct a program in a particular language. The steps of the algorithm are specified using instructions that actually resemble those in your programming language. Pseudocode instructions include a well-defined operations or statements. Programming languages are primarily intended for expressing algorithms in a form that can be executed by your computer, but often used as a way to define or document algorithm. Pseudocode also helps us analyze the time required to solve a problem using algorithm, independent of the actual programming language used to implement your algorithm. This is one such example of your pseudocode. This particular pseudocode locates the largest number in your finite list. As you see on this given particular pseudocode, we're primarily concerned with the main body of the program, since this particular subject is not all about programming. Therefore, in order to locate the maximum value found in your finite list, we simply look at the main body of your program. Here, your corresponding program uses a variable called max in order to store the largest number in the list, and assumes that the first number in your array of integers is the largest number, which is called A1, and then goes through a loop comparing your variable max to every item in your list. And as seen on the looping statement, it includes a conditional statement that if the value in your variable max tends to be less than your next value, then your corresponding variable max takes in that value. So at the end of the loop, your corresponding variable max will now contain the largest element in your list. Flowchart. A flowchart is another more systematic way of showing your algorithm. However, in this particular type of algorithm, it basically shows you a diagrammatic representation of the step-by-step solution to a given particular problem. Symbols are often used to describe different elements in your particular flowchart. Flowcharts are also used in analyzing, designing, documenting, or managing a process or program in various fields. This is an example of a program flowchart. I'm sure you're familiar with this since you're already through with CP1 to 112, which is computer fundamentals. Therefore, I don't need to cover different symbols used for specific parts of your given program flowchart. Note that your program flowchart is exactly the same as your pseudocode seen on the right, which means that this particular flowchart operates in the same manner as your pseudocode. This is an example of a process flowchart. Here, you will notice that there are some symbols that are dedicated for process flowcharts only, that are also used as flowchart. There are some properties that algorithms generally share, and these properties are the input, the output, definiteness, correctness, finiteness, effectiveness, and generality. Here are some sorting algorithms that I have taken out from the book. Sorting algorithms eventually arrange your corresponding list and put them in a given particular order, whether it's increasing, numeric order, alphabetic order, and so on and so forth. Sorting is very important because a non-trivial percentage of computing resources are devoted to sorting different kinds of lists, especially applications involving large databases of information that need to be presented in a particular order. Sorting is also important because an amazing number of fundamentally different algorithms have been invented for sorting. Their relative advantages and disadvantages have been studied extensively. Sorting is important because they are very useful to illustrate the basic notions of computer science. Here are some common sorting algorithms. You have the bubble sort. A bubble sort is a simple sorting algorithm that works repeatedly by stepping through adjacent elements in your particular list, comparing these pair of adjacent items if they are in the correct order. If they are in the wrong order, swapping is done. The pass through the list is repeated until no swaps are needed, which indicates that the list is eventually thoroughly sorted. This is one such example of your bubble sort algorithm, which actually arranges this set of single-digit integer numbers in incrementing order. The list compares the first two adjacent numbers 3 and 2. He eventually obtains that these particular items are not in the correct order. Therefore, he swaps them and then moves on to the next adjacent number. Note that since the specified order is incrementing, therefore, the particular algorithm knows that the higher number, the number on the top, must be less than the number at the bottom. Hence, on the next adjacent values 3 and 4, no swapping is done. The next adjacent numbers are compared 4 and 1, swapping is done because they are in the wrong order. And finally, 4 and 5 are in the correct order. Therefore, no swapping is done. After which, the highest number, which is 5, seen at the bottom of the list, eventually is locked into place. And then the process is repeated again for the remaining values. So again, checking the first two adjacent numbers if they are in the correct order, and checking 3 and 1 if they are in the correct order. They are in the wrong order, therefore swapping is done. And then checking the next adjacent values, which are 3 and 4, and they are in the correct order. Therefore, no swapping is done. So then, by the end of the second pass, the values are now arranged as 2, 1, 3, 4, and 5. And in this case, 4 is now locked into position. And then on the third pass, the first two adjacent values are then compared. 2 and 1 are in the wrong order, therefore swapping is done. Then 2 and 3 are then checked. And then the next higher number, which is 3, is now locked into place. So by the fourth pass, he then checks the first two adjacent numbers and finds that they are no longer in, they are in the correct order. Therefore, no swapping is done. And so as the remaining numbers are already locked, therefore the remaining values are now in the correct order. Hence, the corresponding algorithm terminates. This is an illustration of how your particular bubble sort works. You will then notice that after one complete pass of your respective bubble sort, the highest number in the list is then placed on the rightmost part of your list, since this bubble sort arranges your values in incrementing order. And after one complete pass, the highest number is locked into place. And then the bubble sort repeats the process again, checking the first two adjacent values if they are in the correct order, and so on and so forth. And again, you will notice that on the second pass, the second highest number on the list will then be placed right next to your highest number and is locked into place. After locking that into place, the bubble sort repeats the process again on the first two adjacent numbers until all the values eventually are locked into place. That's how your bubble sort works. Another sorting algorithm is known as your insertion sort. An insertion sort algorithm is uh, a process whereby your algorithm begins with the second element. The insertion sort compares the second element with the first element, and if the second element is less than the first element, the insertion sort algorithm places this in front of your first element and then goes on to check the third element. On the third element, he then compares that to the second and the first element using greater than or less than. If your third element is less than the second element, he then inserts that before the second element. And then compared again, the third element is compared to the first element. And if it's less than the first element, he then inserts that in front of your first element, and so on and so forth, until all the corresponding elements are eventually sorted. This is an example of your corresponding insertion sort algorithm. So he checks the second element and inserts that in the first element because your second element is less than the first. And then the third element is then inspected. Since it's less than the second element and the first element, it's inserted in front of the first element. As you can see, as the insertion sort process goes on and continues, the entire process is simply inserted on each of the corresponding list of values. Therefore, one complete pass of the insertion sort eventually sorts out all the items in your list. Another sorting algorithm is known as the selection sort algorithm. The selection sort algorithm begins by looking at the least element in the list, and this element is then moved in front of the list. Okay, and then the algorithm goes back to the list, looking again for the lowest value in your corresponding list, and then placing them on the second position, and so on and so forth. This is an example of your selection sort algorithm. Searching algorithms. There are several searching algorithms that are seen in the book. However, here I only included the linear search, which is a very common searching algorithm, which is referred to as the sequential search algorithm. This is a method for finding a particular value in the list that consists of checking every element in your list one at a time in sequence until the sought value or the desired value is found. The linear search is basically the simplest searching algorithm and often referred to as the brute force searching algorithm. Its worst case analysis is proportional to the number of elements found in the list, which implies that if there are 10 items on the list, therefore the sought value is compared 10 times. That is, if the sought value is seen at the last part of the list or at the end of the list. Therefore, this particular searching algorithm is not very effective since if you have more elements in the list, turns out it will take more time to search your corresponding array. The general search problem is often described to be locating the item in your list based from distinct elements and returning the position value of your corresponding element. If that particular element is not found, then a value of 0 is returned instead. This is an example of your linear search. Note that whether the list is sorted or unsorted, this particular searching algorithm works and goes through every item in your list, comparing the sought value, in this case 33. The binary search algorithm this time is a more effective method in searching your corresponding list. It inspects the middlemost element of your given sorted list. If the corresponding sought value is equal to the middlemost value, then the item is found and the position is returned. Otherwise, the algorithm either looks at the upper half or lower half of your corresponding list, depending if the value of your middlemost value turns out to be greater than or less than the sought value. The method actually reduces the number of times you need to compare your sought value every time by a factor of 2. Hence, most programmers often refer to this as the dichotomic divide and conquer search algorithm. This is an example of your binary search. Given a sorted list of values, he then looks at the middlemost element, searching for 47. And if the middlemost value turns out to be not equal to 47, he then checks whether it's greater than or less than to determine which of the part of the list he continues searching. And in this case, he continues searching on the upper half of the list. On the upper half of the list, again, he looks for the middlemost element and compares that to your sought value. Looking at the corresponding process, the system only compared your sought value 47 3 times. When comparing your linear search to your binary search, basically, this is your comparison. And one such example here is a sorted list of array numbers, and we're looking for the value 37. You will notice that in using the binary search algorithm, the value 37 is found by only comparing your sought value 3 times, as compared to the linear search comparing your value 11 times. Complexity of algorithms. Complexity of algorithms often refer to the efficiency of algorithms, which involves normally computational complexity. Basically, this is an analysis of the time required to solve your given problem of a particular size. The analyses are often based from different factors. One such complexity is called time complexity. The time complexity is expressed in terms of the number of operations used by the algorithm when the input has a given particular size. The operations used to measure time complexity can be comparison of integers, addition of integers, multiplication, division, etc., etc., or any other basic operations. The time complexity of an algorithm usually described in terms of numbers of operations instead of the actual computer time. This is due to the differences in computational speed of your computers, as well as differences in terms of hardware and software your particular algorithm is implemented. There are several measures of different complexities in your algorithm, which eventually accounts to efficiency of algorithm. However, there is a standard way to measure efficiency on your algorithm. This is done using the big O notation. The big O notation is extensively used to estimate the number of operations an algorithm uses as its input size grows. From this, a computer algorithm is determined whether it's practical to use as its input size increases and to compare which algorithm uses fewer operations. Eventually, this particular basis for your efficiency is based from the input size as well as the number of operations used in your input. Note that a higher value input means more bits, therefore it will take more time to execute that algorithm. And if you have more operations involved in your algorithm, this will eventually take more time also to implement your algorithm. The big O estimates the time complexity of an algorithm used in solving a particular part of the problem. It expresses the time required to solve the problem changes as the input size eventually grows. Therefore, your big O notation subdivides your given algorithm into several complexities. However, big O estimates of time complexity cannot be directly translated into actual amount of computer time used. However, the time required for an algorithm to solve a problem of a specified size can be determined if all operations are reduced to bit operations used by your computer, as you will learn later in your microprocessor. Another important factor that decreases the time needed to solve problems on computers is parallel processing. These are the common terminologies on your complexity of algorithm through big O notation. So you have the constant complexity, the logarithmic complexity, the linear complexity, the linear-arithmic complexity, the polynomial complexity, the exponential complexity, and the factorial complexity. This graph actually shows you the corresponding difference in the behavior of your different complexity functions as your input size n gets larger, seen as the y-axis here on this given graph. The big O estimates computer time based on this corresponding complexities of algorithm as seen on the input size if you know the operating frequency of your given computer. As such, you can actually determine how long it takes to implement a given particular data size based from a given particular complexity of your big O notation. This ends the module. On this module, we have discussed the following definition of your algorithm, the different ways to express your algorithm. We looked at different sorting algorithms and searching algorithms, and we determined efficiency in measuring your algorithm. Thank you for listening. Sige, o higa ka na dyan.